Alright, so for the last little bit about vectors, one thing that we haven't discussed yet is the angle between two vectors. So we're going to call this angle between u and v here, vector u and vector v, to be theta. And if we set this up with this vector w up here, creating a third side of a triangle, we can talk about this in terms of the law of cosines. So we can now look at where vector u is. It has its own magnitude, so this would be the magnitude of u. Down here, of course, would be the magnitude of v along the bottom of this triangle. And then this one here is the magnitude of w, and we'll talk about that one, well, right now. So when you're talking about magnitude of w, it's going from one end of the vector v to the other end of the vector u. So it started at v and it ended at u. That is the subtraction definition of u minus v. So w is just u minus v. And technically it doesn't matter if you flip it over, it'll still give you the same result as v minus u after we do all our fun math. So let's get some math out of the way. Let's talk about the magnitude of u. Now u itself is going to be the magnitude of the components, and since we don't know what the numbers are, we'll just call it u1, u2. And then this is going to become the square root of u squared, u2 squared plus u1 squared. And then the same thing is going to happen for the magnitude of v. We're going to get the square root of v2 squared plus v1 squared. And then the magnitude of w is the same thing as the magnitude of u minus v. So this one's going to be a little bit different. To get the magnitude of u minus v, it's going to be u1 minus v1, comma, u2 minus v2. Okay, and then the square root is just going to be a little bit longer. It's going to be u2 minus v2 all squared plus u1 minus v1 all squared. Alright, so these are the three sides. So if we label this one A and label this one B and label this one C, then we could write out the law of cosines. And do some substitution. So C is represented by, change colors here, this ugly square root, but it's going to be squared, so the square root goes away, and we're going to be left with u2 minus v2 squared plus u1 minus v1 squared. All right, equals, so we're up to this point. And then a squared plus b squared, so we're talking about these two square roots, but being squared, the square roots are going to go away. So we're going to get u2 squared plus u1 squared plus v2 squared plus v1 squared. And I'm going to leave the minus 2 and the a and the b are the magnitude of u and the magnitude of v. I'm going to leave it in this notation. And then finally, cosine of the angle that is between the vectors. Alright, so it's a long, ugly mess mathematically, but it'll simplify in a few seconds. So if I square out as much as I can on the left-hand side, and then see what happens. So this becomes u2 squared minus 2 u2 v2 plus v2 squared. That is this guy so far. Uh-oh. And then the second term here, I'll do it in a different color, is going to be plus u1 squared minus 2u1 v1 plus v2 squared. All right, and that is this guy being squared out. All right, and then the rest of it is going to kind of stay the same. On the other, oops, on the other side, we have u2 squared plus u1 squared plus v2 squared. I don't know why I put it in the opposite order. It really doesn't matter. Minus 2 magnitude of u, magnitude of v, multiplied together, of course, times cosine of the angle that separates the two vectors. And then the fun begins. On this side, there is a u2 squared. On this side, there is a u2 squared. They go away. They're both positive. If I subtract it from both sides, it disappears. This side has a u1 squared. This side has a u1 squared. So again, those are going to cancel. This side has a v2 squared. Here's a v2 squared on the other side. They're going to cancel. And here we have that should be a v1. Here we have a v1 squared, and here we have a v1 squared, so they're going to cancel. And that one's definitely v1 because that's where it came from, v1 squared. All right, so they're going to go away, and then you're left with a lot less. Negative 2 u2 v2, negative 2 u1 v1, and then on the other side, negative 2 magnitude of u, magnitude of v, cosine of the angle that separates the two vectors. All right, and then they all have a negative 2, so I can get rid of that. And I'm going to change my order back the way it should have been. u1 v1 plus u2, u2 v2 is equal to the magnitude of u, the magnitude of v, cosine of theta. So if I know what my two vectors are, I can actually go through and plug in the components for the vectors into this formula and then solve for theta to come up with the angle between the two vectors. But there's actually something more important going on here. We're going to define the two sides of these equations commonly because, well, they're equal to each other. And it's going to be called a dot product. So u vector dotted, it looks like multiplication, but these are not numbers, they're vectors, so we have to call it something different. It's a dot product. We're going to let it equal u1 v1 plus u2 v2 as one possibility, but we're also going to define u dot v as the other side of the equation, which is the magnitude of u, magnitude of v, cosine of theta. Now, defining it this way allows you to come up with a numerical answer and then substitute it in here, and then you can solve for cosine of theta. But u dot v defined as u1 v1 plus u2 v2 is really important and it has a lot of applications. This formula down here is generally used to find the angle theta. So let's say we want to just figure out how to find the dot product. So here I have, find u dot v, u1 v1 plus u2 v2. So basically it's the product of the first components plus the product of the second components. So if we expand that out to what we have up here, we're going to get negative 3 times 2, that's the product of the first components, plus 5 times 4. And I should have put parentheses here. It's really best if you write it this way in case there's negatives involved. It's the only mistake I've ever seen here is like a sign mistake. And then this turns into negative 6 plus 9, which turns into 3. So u dot v, when you find a dot product, it becomes a scalar. So before, when we added two vectors together, we got a vector. And if we subtracted two vectors, we got a vector. So and if we scalar multiplied a vector, we got a vector. So here's a case where we're doing an operation on two vectors, but we're ending up with just a number, a scalar value. All right, then the next question we could ask is, what is the angle between the two vectors? So find angle between u and v from up above. Alright, so if I'm going to find the angle between u and v, then it switches over to the other formula. So the formula is u dot v is equal to magnitude of u times the magnitude of v cosine of theta. And plug in what we know. Well, I know u dot v is just this number 3. Then I just have to find the magnitude of u and the magnitude of v. So if I go back up to the top, and find their magnitudes, the magnitude of u is going to equal the square root of negative 3 squared plus 5 squared, better known as 9 plus 25, better known as square root of 34. All right, so the magnitude of u is that, and then the magnitude of v is going to be 2 and 4, so the square root of 2 squared plus 4 squared, which is 4 plus 16, which is the square root of 20, better known as 2 square roots of 5. We don't have to be so precise. Since we're going to be finding theta using a calculator, you can leave it as the square root of 20. And it actually might make things better to leave it as the square root of 20 in this case, because you're going to be multiplying it by the square root of 34. So if you have the square root of 34 times the square root of 20 cosine of theta, to make sure we don't make any silly calculator mistakes, it is better if you multiply the two square roots together. So this would become the square root of 680, and that way it's contained within one operation rather than two separate things. Because eventually, to solve for theta, we're going to have to divide by either the product of those two numbers, and then you have to remember to put parentheses around the whole thing, or just write it as a single square root and then just divide the single square root across. So we're going to get cosine of theta is equal to 3 over the square root of 680, and then we're going to do cosine inverse. And in degrees, that's 83.4 degrees. So this would be the measure of the angle between the two vectors. So if I drew it, just a quick little sketch. See if it's relatively messy. So negative 3, 5. So it'd be 1, 2, 3, 1, 2, 3, 4, 5, someplace up here. So my vector would be there. And that would be u. And then v is just 2, 4, so 1, 2, and then 4 up is over here. And you can kind of see that the angle between these two vectors is really close to a right angle. I mean, not super close, but at least 7 degrees. And the measure of this angle here would be 83.4 degrees, the angle between the two vectors. And this, of course, is v, vector v. One of the important takeaways from a dot product is a special case of two vectors. So if u and v are two vectors such that, let's see if we can draw this nicely, the angle between them is a right angle. So theta in this case is equal to 90 degrees. Normally we would call these lines type things perpendicular, but vectors have their own language. So perpendicular for lines becomes orthogonal for vectors. Orthogonal is just vectors at right angles. So the vectors have a right angle in between them. So if you did solve this equation up here, you would find that theta would be equal to 90 degrees. So the second part of this is if cosine of 90 is equal to 0, then when u is orthogonal, I'm not going to spell out the whole word, to v, we get u dot v is equal to 0. And that 0 vector, this, remember, dot products is scalar numbers, regular old real numbers. So if you have two vectors that you do their dot product and their answer is 0, then you know for sure that they are orthogonal vectors, and basically you can think of them as perpendicular. And for applications, this becomes really important. So let's say we have these two vectors, u being -2, 3, and v being -6, -4. Now, just a reminder, you can also write this as -2i plus 3j, and this one over here is -6i minus 4j. So whether it's written ij notation or component notation, personally I like component. I find it much easier to see the numbers rather than the i's and the j's. But either way, if we do u dot v in this case, what we're going to end up with is -2 times -6 plus +3 times -4. So this would be 12 minus 12, which is equal to 0. And then we can say, therefore, u is orthogonal. I spelled that horribly wrong. To v. And that's all we need to know. So another topic that includes the dot product is this idea of a projection of a vector. Now this comes in handy when we start talking about an application called work. And what happens is you need to change a force's direction. So like, for instance, I have this u here going off in that direction, and I want to know how much of that force going in that direction is applied in the direction of the other vector v here. So I want to know how it's applied in this direction. All right, to do that, it's actually not too hard. First thing, notice I've drawn a perpendicular. Oops, wrong color. Drawn a perpendicular here from the tip of u down to the vector v. So I kind of think of this as the sun is up here shining, and it's shining directly down onto vector u so that it is perpendicular to the vector v. And if you do that, then the shadow is going to end up down here on vector v, which is my next picture. So that's kind of how I think about it. Now, if vector v is pointing in a different direction, for instance, let's say, let's go back here, this guy. And let's say vector u is pointing over in this direction. Well, the sun is still going to be up here shining down, and vector v can be extended by going to -v, and then our shadow would be on this side of the picture, and this would be the projection on that side. So it works no matter if u and v are above each other or the angle between them is obtuse. All right, so let me get rid of my secondary sun. All right, so let's talk about the second picture. In the second picture, the angle here in this triangle is theta. The side length of vector u is the magnitude of vector u. And I need to know what is the length of this thing that we're going to call a projection. So to find the length of that side, let's call it x for now. We're going to have x here, we have the magnitude of u up top there, and we have an angle in between them, and that's adjacent over hypotenuse, which is cosine. So we're going to set up cosine of theta is equal to x over the magnitude of u. And therefore, that side is going to be, kind of reminds you of polar coordinates again, the magnitude of u times cosine of theta. So that is the amount of force that the u vector is going in the direction of v. And it's not always force, but I like saying force because it's easier to kind of understand pulling something with a with a specific force. Delete that. In direction of v. And this is u's force in the direction of v. So we're just going to call that a fancy name and call it literally, well, up here, projection. All right, so that's the amount of force in the direction of v. So the next thing is we're going to go back to a topic that I discussed earlier about unit vectors, that if we create a unit vector, then we just have to multiply by its magnitude to get it to be the right length. So I know the direction I want to go is in v, so I need a unit vector for v. So unit vector for v, so I can scale it to the size that I want, which is the magnitude of u cosine of theta. All right, so to find the vector, unit vector for v, we're going to take v and divide by its magnitude. Trying to draw my v's this way. All right, so there's my unit vector for v. So this is the direction of the vector that I want. And up here, this is my magnitude of the direction I want. So since a vector is magnitude and direction, I'm going to just multiply them together. So the vector I'm looking for, we're going to call, let's go green here, the projection of u onto v. This is u onto v. And it's really important the order that these two letters go in, because u is the one we're trying to find whose force is going in the direction of v. So if I switch them, then I'm projecting v onto u, which would be over here, and it'll be a bit longer than what u is. Okay, so then this projection of u onto v is going to equal the product of the two things that I have up here. So I have the magnitude of u cosine of theta times a unit vector, so times the unit vector v over the magnitude of v. That doesn't seem very nice. All right, so let's kind of neaten it up a little bit. We have to kind of go back and write down a few other formulas. And one of the formulas is that u dot v is equal to the magnitude of u times the magnitude of v cosine of theta. And if I use this formula, I have part of it. I have this part right here. The only thing that is missing is the magnitude of v. So if I multiply that thing by the magnitude of v, I'd have to also multiply the bottom by the magnitude of v. So I'm going to take this whole thing and multiply top and bottom by the magnitude of v. So I can introduce a dot product. So then that becomes the projection of u onto v is equal to. So let's see here. Let's get things in order. Kind of circle a few things. This is a scalar. This is a scalar. This is a scalar. So what I'm going to do is I'm going to group all my scalars to the left. All right. So then this becomes, let's see here, the magnitude of u the magnitude of v cosine of theta. All right, so that takes care of everything that's in the numerator, all over the magnitude of v squared, and then my vector. So this whole thing that I've written so far is just the scalar part of it. This is the length of my vector in the direction of v. So this takes care of a few things. It takes care of the unit vector of v. It's buried in the vector of v divided by the magnitude of v. But it also kind of separates all the scalars from the vector being him. All right, and then magnitude of u, magnitude of v, cosine of theta, I can replace with u dot v. So my final formula is the projection of u onto v is equal to u dot v all over the magnitude of v squared times the vector v. So remember, this is a scalar, and the other one, this over here, is your vector. So our answer is going to be a vector, which is kind of nice because that's what we wanted. And it's going to be literally this vector right here when we're all said and done. So this is called the projection of a vector onto another, and it forces us to look at it as how much force is going in another direction. So here I have two vectors, vector u and vector v, and I've drawn a picture of the vectors in a coordinate system. So u ends at 1, 6, and v ends at -5, -2. And I want to find the projection of v onto u. That means I'm going to make a shadow of v on top of the line that's generated by the vector u. And if you notice here, if I try to shadow v onto u, there's nothing, there's nothing to shadow on. It kind of keeps going on forever. So I have to change this picture just a little bit so that it has something to create a shadow on. So I've created this other picture by just including the vector -u going in the opposite direction. And technically it doesn't even have to be the vector, it just has to be a line or a ray going on in the opposite direction parallel to u starting at the origin. And now when I do my shadow, it has some place to land, and this projection is formed along that opposite extension of u. So when I find this projection, it's going to be this little pink vector down there in the third quadrant. So by the formula, the projection of v onto u, the top is never going to change. It's going to be u dot v no matter what order the u and v is next to the projection. It's the bottom one that you have to be really careful about. It is, in this case, the magnitude of u squared times the direction I want to go in is along the u vector. So this is the projection of v onto u's formula. So whenever the small letter is here, that's the one that's going to get repeated the most in the formula. Notice it shows up 3 times. All right, so we need to find u dot v to start this formula off. And u dot v is going to be 1 times -5 plus the components in the second position multiplied together, 6 times -2. This will give you a grand total of -5 minus 12. Oops, that's an ugly 5. And that's for a grand total of -17. So u dot v is going to equal -17. All right. And then we need to find the magnitude of u without the square root because it's going to get squared. So the magnitude of u squared is going to equal 1 squared plus 6 squared. So that's going to be 1 plus 36, better known as 37. So my projection of v onto u is going to equal the dot product, negative 17, divided by the magnitude of u squared, which is 37, and then I'm going to multiply it by the vector u, the one we want to go along, which is 1, 6. Now notice one thing about this. The sign of this is negative, which makes absolute sense, because if it was positive, we'd be going in this direction. And I want to be going in the opposite direction. So that negative is at least telling me I'm going in the right place. And 1, 6, it'll be negative 1, negative 6 would be pointing down into the third quadrant. All right, so this is the projection of u onto v. Now there's one other thing that generally we want to do when we find these projections. A projection by itself is not so important. What's interesting is what's called an orthogonal pair. And what that represents is I want to add the projection that I just found to another vector to end up with this v. So this v is the diagonal. And one thing to notice here is this is a right angle. So if I'm looking for a diagonal, it's going to have to be in a rectangle. So that rectangle is going to be something like this. And this is the other vector that I want to find, is this one right here. Now there's two ways to go about this. We can go the long way and find the projection of v onto a perpendicular vector or orthogonal vector to u, and that gets kind of tricky. Or we could kind of be a little bit smart about it. Let's call this vector v sub 2. Let's call the projection v sub 1, vector 1 and vector 2. And these two are going to add up to the vector that I started off with, which was v. So I'm going to get v is equal to v1's vector and the sum of v2's vector, because that's what it means to be a sum of vectors. It's the diagonal of a parallelogram, in this case, a rectangle. So I know what v is equal to. This one is negative 5, negative 2. I know what u1 is equal to. It's this mess up here, so I'm going to expand it out. It's negative 17/37, comma 6 times 17, negative 102. So that would be negative 102/37. And then I have my vector 2, which I don't know the components, so let's just designate them by a comma b. So I need to find a comma b to find this orthogonal vector. Alright, so to solve this, I'm just going to get a comma b by itself, and I'm going to move this other thing to the other side. So I get negative 5, negative 2, minus the vector negative 17/37, comma negative 102/37. And this is going to equal a comma b. Now, if it gets confusing at this point, you can always change everything back into ij notation. This is negative 5i hat, this is negative 2j hat, and then over here you're going to get that negative 17/37 I hat and negative 102/37 j hat, distribute the negative, and combine like terms. But basically what happens after you do all that, you show that this number minus this number is basically what you're looking for the first component. So this will become negative 5 minus a negative is a positive 17/37 for the first component. And then negative 2, negative times a negative is a positive 102/37 is the second component of this vector AB, or in this case, vector V2. So let's see here, let my calculator do the walking. Negative 5 plus 17 37ths. It's not a very pretty number. So this becomes negative 168/37 as the first component, and negative 2 plus 102/37 is 28/37. That actually turned out better. Alright, so this vector represents V2. This vector represents V1, and they're an orthogonal pair. And it's pretty easy to show that they're an orthogonal pair. You just have to multiply things together. Now, since they have a common denominator of 37, we just have to dot product the top. So it would be negative 17 times negative 168. That gives you 2856. I'll write it down here. And then do negative 102 times 28. Times 28. And that gives you a negative 2856. And this would be all over 37 squared if you want to put that in there. But the top's equal to 0, so this becomes an orthogonal pair. It's kind of cool. Let's talk about an application of an orthogonal pair. Let's say we have a weight that's sitting on a ramp, and if this thing weighs 200 pounds, then that force is going straight down towards the center of the Earth, which would be represented by this vector here, this W, which I call W because of its weight. So this weight vector is going straight down, but there's two other vectors that are kind of important. I have this W1 here is the amount of weight is trying to go down the ramp. And then I have this W2 over here is the amount of weight that is being applied directly to the ramp. And it gets split into these two orthogonal vectors. So it's kind of a neat idea that you can separate force into these orthogonal pairs, and these orthogonal pieces usually turn out to be really important. You might remember the cannon example. If you had God, I can't draw. If you had a cannon down here and it's shooting a cannonball up at an angle with so much force, we split it into a vertical force and a horizontal force when we were dealing with parametric equations. And that turned out to be an orthogonal pair of forces for a cannon being shot alpha at an angle. All right. So let's find out what's going on here. Now, one other number that we need to know is the angle of this ramp. So if we're looking for the angle of this ramp, this angle here, let's just call it theta, whatever theta is equal to. And what I need to do is show that that theta applies to my little rectangular setup over here. So if this is theta, then this angle here in the other corner of this triangle that's formed by this shape here, then these two angles, let's call this one beta, then theta plus beta has to equal 90 degrees. Because the sum of all of the angles has to be 180, and I know that this is a rectangle and it's got all these right angle corners. So these are called complementary angles, two angles that add up to 90. That means that this angle here and the beta over there are also complementary angles because they form that right angle there in the corner. So this angle's measurement has to be theta. And that means that this measure of this angle down here is also theta because you have parallel lines and this transversal cutting, and these are called alternate interior angles. All right, let's unzoom. All right, so if we want to find the magnitude of W1, then we're talking about this triangle off to the left, and this angle down here is theta, and the amount of force going down the towards the center of the Earth is that 200 pounds. If we make this weight 200 pounds, it could be anything, a car, a bunch of bricks, or whatever. So when we look at this picture, this side over here is called opposite of theta, and then the 200 pounds magnitude going straight down is the hypotenuse. So this becomes sine of theta. Remember, theta is the elevation of the ramp, is going to equal opposite the magnitude of W1 over the weight of the object, that 200 pounds. So then we get that the magnitude of W1, amount of force going down the ramp is equal to 200 sine of theta. All right. So now if we look at, let's get rid of that part, get rid of that, leave the 200 pounds, but I'm going to write it differently. So if we have 200 pounds going down this side, and we're looking for W2, which is this side of the triangle, and theta is now this angle, then W2 is adjacent, 200 pounds is the hypotenuse, and that's going to be a cosine. So we'd have cosine of theta is equal to the magnitude of W2 vector over 200. And then magnitude of W2 is going to equal 200 cosine of theta. Wow, this again looks a lot like polar coordinates that we were dealing with, seems like this whole chapter. So that would be how much force is going down the ramp. And then this one would be the force into the ramp. And that's how easy it is to find. You don't have to, go into changing everything into vectors and going through all that mess. It's just easier to recognize it as an orthogonal pair. Redoing work, part 2. All right. Normal work is applying a force to an object and moving it in a direction. So let's take a object. Let's just make it a block. And I want to move it along the ground. And obviously there's going to be friction. And you can add wheels, but even then there's still going to be friction. And we're going to pull it directly in the same direction as the motion of the object's going to take. So in other words, I'm going to walk along this horizontal ground and I'm going to pull the block with a horizontal force. So this force is the amount of pull that you're applying to the block. Now if the block weighs like 50 pounds, you're obviously going to have a force greater than 50 pounds to move it because of friction. Alright, so then if we carry this thing a certain distance along the ground with this force, then work is going to equal force times distance. And here I really should say the magnitude of the force, because the force vector is not a number, it's a vector. Alright, so that's what work is equal to. And generally we're going to measure the magnitude of this force vector in pounds, and we're going to measure the distance in feet. And when we multiply these together, we're going to have units of a foot-pound. It's a really strange unit. The metric units are a little bit nicer. I'm quite sure it's like Newton is one of them. All right, so if we make the force that we're applying, change colors here, to this object 200 pounds of force. And the way we could measure that is like a spring measurement system, like you would weigh a fish. And you would attach it to the end of a string, pulling it horizontally in this direction. And you would apply 200 pounds of force. So you'd try to keep the spring measuring 200 pounds while you travel this distance. And if we make this distance 15 feet, then the work done is going to be the 200 pounds times the 15 feet for a grand total of 3,000 foot-pounds of work. So this foot-pounds is just a measurement of work. So it's kind of a neat idea. The problem comes when you do something like over here. You don't always apply forces in the same direction that you're going to move an object. Usually, kind of like if you tie a rope around a rock and you want to move it along the ground, you're going to pull it from an angle. So we're going to apply a force in this direction, but we want the object to move in that direction. So they're not going in the same direction. And that's really important for this formula to work. So one way to take care of that is to call this one the force vector. And then we can call this one down here the applied force vector, what's really going in the same direction as the object is also moving. So I'm going to call that force vector 1. And to get to the direction that I need to move this in, to keep it parallel with the direction, we're going to do a projection. And we're going to drop our vector down, and we're going to create this new force vector going in the same direction as the motion. So even though we're pulling it off angled, we're going to just make part of the force go in the right direction. The other part of it is just going to get wasted by your shoulder. Alright, so to come up with this side, we're going to change everything into magnitudes. So this will have a magnitude of whatever the force vector is. And down here we're looking for the magnitude of our applied force. Or our, what's a good word for it? Our resulting force. There we go, that's a good word. Resulting force. Alright, and then the relationship between the magnitude of the original force, the magnitude of the resulting force, and the angle theta is just cosine. So we're going to get cosine of theta is equal to adjacent, the magnitude of the resulting force, divided by the magnitude of the original force. And then if you solve for the resulting force, you're going to get, let's get away from this orange color, we're going to get the magnitude of the resulting force is equal to the original force times cosine of theta. So this will give us a way of finding the force that is going in the same direction as the motion. And then if I know what this distance that I'm covering, this d, then the work is just going to be this force that I just found, which is the original force cosine of theta. That would be your force, and then times distance. So it gives you this formula for off-angled forces, where F is the original force vector, and cosine of theta just drops it down to be the right size for the resulting force. Alright, so another little side note on this formula is if d was also written as a vector, this distance that we're covering can also be written as a vector. If I could write that as a vector, then we would have work is equal to the magnitude of the force vector cosine of theta times the magnitude of the distance vector. And if I rewrite this, this becomes the magnitude of the distance vector times the magnitude of the force vector times cosine of the angle between these two vectors, because theta is literally the angle between the two vectors. And this is identical to the dot product definition between vectors. So we can say finally that work is equal to the force vector dotted with the distance vector. So if you're working with pure vectors, this becomes the easier formula. If you're working with a magnitude of a vector and a physical distance, a scalar distance, then this is the formula you want to use, as long as you know what cosine of theta is equal to. So just for fun, this idea in calculus becomes really important, and even more so in differential equations. That the idea that if you have a force and a distance in vector terms, then to find the work done, it's just the dot product. So here we're going to say, well, the work is equal to the vector of the force and the vector of the distance dot product. So we're going to get force, which is 2,7, and it's being applied over a distance along 512, kind of like the hypotenuse of the triangle. So we find the dot product. This becomes 2 times 5 plus 7 times 12, which becomes 10 plus 84. So the work done is 94, and then just make a few assumptions that this thing is measured in pounds and this thing is measured in feet. Then this would be a foot-pound. So 94 foot-pounds of work is the system of pulling something with a vector of 2, 7 along a vector of 5, 12. So it's an easy calculation. So let's talk about work in a strange way. Maybe we're pulling an object up a ramp, so like a radio flyer, and we're trying to pull it up a driveway. So this is going to be an off-angled motion with an off-angled force in the direction of the motion. So one of the lines you want to draw in here is a parallel line that starts where your vector is, going in the same direction as the ramp. So that forces this angle also to be no, doesn't force anything. So then you can technically ignore theta completely, because that's not relevant in the discussion. What's relevant is the angle up here, the angle between you and the horizontal motion. So it goes back to what we were just doing in the previous example. So this becomes the work done as you pull this thing up the ramp is equal to the magnitude, let's call this force, of the force vector times cosine of, in this case, beta, times the distance that it's traveled. So it's irrelevant that you're going up a ramp. It's kind of weird thinking about it that way, but that's what's happening. So here's an example. A force of 100 pounds is being applied at 65 degrees off of the horizontal while moving a block 25 feet up a ramp with a 20 degree incline. How much work will be done? So let's take this apart little by little. So first off, force being 100 pounds, that means this force vector, its magnitude is 100 pounds. Okay. The angle being 65 degrees off of the horizontal, you have to start thinking, well, here's where the force is being applied to the block, and the horizontal direction is parallel to the ground. So you got this kind of imaginary line going across your picture. Then this angle here has to be 65 degrees. All right. And then we are going to move 25 feet up the block, or up the ramp, and it's got a 20 degree incline. So this angle here is 20 degrees. So what we want to do is, the main point is to get the force going in the same direction as the motion. Well, the direction is going to be parallel to the ramp. So the ramp is going in this direction here. So I need to make sure that my force is being applied in this direction. So this is just the direction of the force, not necessarily the magnitude of it. And that is parallel to the ramp. So that means this angle here is going to be congruent to our 20 degrees down there because they're corresponding angles. So this would be 20 degrees. So that means that the angle that we're going to be working with between the force vector and the direction vector is going to be the difference of these two angles. It's going to be the big 65 degrees minus the 20 degree ramp. To get us going in the right direction, this would be 45 degrees. What a nice angle. So if we're going to use our formula, then work is going to equal the magnitude of the force vector in the direction, of the motion, which would be the cosine of the angle between the force vector and the direction of the motion, and that angle is 45 degrees, times the distance, and the distance was 25 feet. So this becomes, I forgot to put the magnitude of the force in there. This would be 25 times 100, which is 2500, and cosine of 45 is the square root of 2 over 2. So the work done is going to be 1,250 square roots of 2 foot-pounds. 1250 square root of 2. So that's approximately 1768. So this would be 1768 foot-pounds of work has been applied to this object to move it up the 25 feet.